Hi everyone and welcome back to Spherical Chicken in a Vacuum. Today we are going back to the topic of the last two lessons, which is amorphous materials, and I want to focus only on glasses and not just any kind of glass. I want to speak about silicon-based glasses, which is the most common type of glass that you can actually find in everyday's life. There are so many other categories, there are so many groups, and we just don't have enough time today to discuss about all of them. Maybe in a future lesson, probably, we will speak about other types of glasses, but just bear with me for today, okay? So, I started again from the basics. Silicon-based glasses are mainly made of two elements, which are silicon and oxygen. This is because they are based on basically silicon oxide. And what happens is that each atom of silicon can be connected to four atoms of oxygen, and they form this tetrahedron. And of course, each one of these atom of oxygen has another bond, and as this bond goes to another silicon, so to another tetrahedron, and this generates this three-dimensional structure in which every tetrahedron is connected to four tetrahedron, and it gets very messy and very difficult to represent in a 2D drawing like this. So I will not use it. Also, there is another problem. This is the basic unit of the silicon tetrahedron, but we have other elements in glass apart from oxygen or silicon. We can have phosphorus, sodium, calcium, boron, lead, uranium, germanium, potassium, magnesium, aluminum, and these are not even all the elements, just the ones that I remember when I made this graph. Okay, so what we'll be using is a simplified structural representation that is two-dimensional. So we will do something like this. For example, this is for quartz, which is the crystalline, one of the crystalline forms of silicon oxide. And you can see that each atom of silicon, which is blue, is connected to three atoms of oxygen, which are red. So one oxygen is missing. Why? Because the last oxygen goes in the other direction, in third direction. So it goes outside of the graph. So just keep in mind that this is a two-dimensional representation that lacks some of the bondings. Okay? And if we look at quartz and we discuss about quartz properties, well, basically quartz is pretty strong as a ceramic material. Its softening point is very high, meaning that it takes quite a lot of energy to melt quartz. Its optical properties are good, and its chemical resistance is also good. But all these properties depend on the purity of quartz, and there are basically two different groups of quartzes. We can have the natural occurring ones, and we have the ones that we basically built up in a laboratory, which is not so easy. And the level of purity has a big influence on these properties. So you see these these bars here, but they are not representative for all forms of quartz, because depending on the number of defects and the type of defects, the properties can go down. This is not the maximum properties, let's say. Okay. And this is nice, organized, crystalline, and we wish everything was this clean in material science, but it's not. And when you mess up with quartz, you take your box of atoms bonded together and you shake them. What happens is that you obtain fused silica. Fused silica is what you obtain when you when you lower the temperature of your melted silica, not low enough to form quartz. That's not just a matter of temperature. There are also environmental conditions. There's also pressure, etc. But the point is, silicon and oxygen want to tend to form an amorphous structure, which is something not well organized like this. Okay, which is difficult to represent even in two dimensions, because you need to be careful when you connect all these spheres, balls, and sticks together. Again, 2D representation, every blue atom, which is silicon, has a one more connection somewhere. If we look at fused silica, the fused silica we usually produce is a high strength material with a very high softening point, great optical properties for transparency, for example, not from the refraction index point of view, but we will discuss about it later. And it's very, very chemically resistant. That's why we use it to contain actually aggressive substances. We use it in high temperature applications, windows for ovens, and things like this. It has a high melting point, a low thermal expansion, so it's ideal for high temperature applications. But in the history of humankind, for millennia, we could not produce fused silica. This is because we needed a temperature what was basically impossible to achieve with the means that we had for most of our history. If I remember well, just to start being able to work with fused silica, you need to go at least 1,600, more or less, Celsius degrees, which is more than what you need to produce steel. So you can understand how difficult it is. Also, you need to work with a high purity material that is difficult to extract and purify and actually work with, because you see all these bondings here. It's extremely dense in the number of bondings for unit of material, let's say, is very high, meaning that this material is viscous, this material is resistant, this material is difficult to work with. Luckily, in human history, we didn't have to work with fused silica. But since I don't like this representation, but you can find this kind of representation everywhere on the internet, you don't need me to show you the structure of fused silica. What I want to propose to you is a different representation based on piping. And it's a little bit unusual, so bear with me. So if we represent our silicon as a T connector and our oxygen as a tube, we can make this beautiful and simple and easy to understand bidimensional representation of fused silica, in which, of course, the oxygen has two connections, two bonds. That's why it's a tube, because it connects two parts, and the silicon has three, actually four, but one is in the other dimension, three connections, so it's a perfect T block. So the structure, the network of fused silica is represented by where the liquid can go inside of this piping in the network. This works very well in my idea, especially for simple glasses. As we go into more complicated one, it gets a little silly, but still it's a good representation, easy to follow, I think. Let me know in the comments if you like it. So for most of human history, this was not glass. This was not the glass we used, because it was too high melting point. Its melting point was too high. So what we work with is what we call soda lime glass. In soda lime glass, we have other atoms like sodium and calcium that act like cups and close the piping, basically. Okay, they take the position of the silicon, but instead of connecting the network together, they stop the network. So stoppers, basically. And sodium can only stop one piping at a time, meaning that the one in the corner, in the upper left corner, is actually two atoms of sodium. But calcium, because of its valence, it can stop two pipings with only one atom. And this is what we work for most of the human history, because it melts like 700 degrees, but depends a lot on how many of these sodium and calcium defects you put in your glass structure, because they are actually defects. They interrupt the network. They ruin everything from the beauty of the structure point of view. And the presence of these lowers the melting point, lowers other properties, lowers also the optical properties. If you put too much of this garbage inside of your glass, you cannot even make glass anymore. So it's the reason why I'm using bars to represent the properties is that compositions of glasses can vary a lot. So to give you numbers would be wrong, basically, because I cannot give you precise numbers for every type of glass. Okay. So in this case, soda lime glasses, we lower the melting point, we put garbage inside, sodium and calcium and other things like this inside to stop the network. And this makes the material softer, easier to work with. We lower the viscosity, and that's what we work for bottle, windows, pieces for decoration and things like this in most of the human history. And if you think about what you can find in the museums, the optical properties of the most of the glass we had during human history is very low compared to modern glasses. So this is because also, not just because of bubbles inside of the glass, but also because of the chemical composition. So this kind of glass is weak, easy to melt at even a low temperature. Optical properties are average. I mean, we use it for windows, and it's okay. But if you put like many windows one after the other, you see that the transparency is soon lost or decreased, etc. And it's a good chemical resistance. I mean, it's not super resistant to aggressive chemical substances. Okay, and again, everything depends on the composition. So old windows are much lower quality than modern windows, for example, even if all of them are soda lime glass. Okay. Then we can introduce another type of connector that goes in the same spots of the silicon. So it's part of the network. It does not interrupt the network. And this is boron. Unluckily, boron has one less, luckily or unluckily, because it actually has more advantages than disadvantages, maybe. Has one less connection, so it usually has 3, but one will be outside of this representation. Let's imagine that it's it's going inside of the drawing or coming outside of the drawing, okay? And boron glasses are pretty useful, actually, because boron glasses are strong, fairly strong, fairly high melting point. I mean, it's much more difficult to make boron glass than it is to make soda lime glasses. Properties are not so bad, and they're quite chemical resistant. So when you cannot afford to use fused silica because it's crazy, if you go online and look at the price of fused silica, it's incredible. You can use boron glass, and we do in laboratories. In my laboratory, in most of chemistry laboratories, we have beakers that are made with boron glass. There's many commercial names like Durex, Pyrex, and etc., depending on details of the chemical composition and the producer. And the properties are fair. I mean, I say here that the strength is high, but still, if a beaker falls to the ground, it shatters. I mean, it's strong for a glass, it's stronger than a bottle of the same thickness, let's say, okay? Soda lime glass of the same thickness, okay? Decent optical properties. Chemical resistance is good, and that's another good reason to use it in a laboratory equipment. And another application is for things that go in the oven, even in your kitchen. So this is because it's very resistant to thermal shock. It can go to high temperature to low temperature without breaking. It's something that soda lime glass cannot do. If you put your drinking glass in the oven and then immediately you put it on the sink, the metal sink, it will probably shatter because of the thermal shock going from high temperature to low temperature, if it doesn't break in the oven. This does not happen so easily with boron glass. It's not immune to this phenomena and depends also on the composition, but boron glass is resistant to what we call thermal shock, which is one of the main selling points for boron glass. Because it's expensive, as you can see. Softening point can be considered not proportional, but price is strongly dependent on the softening point, more than on the chemical composition itself. Then we have something that makes a little less sense in my representation of piping, and it's aluminum, because aluminum can act both as a stopper, so interrupting the network, or as part of the network. It can form network or it can modify network, and that's a little messy to represent. So the best idea that I had is to represent it as a valve. Then it can be either open or closed. It's a little difficult to imagine that the aluminum switch is from interrupting the network to forming the network during in service. Okay, let's imagine that when we put it inside of a structure, it's either open and closed. It has three connectors, but in two-dimensional representation, we only see two because one is going inside or outside of the drawing. Okay. And we use aluminum glass to produce a lot of things. Also, the cell phone covers is fairly strong. It has a fairly high softening point. Optical properties are decent, and chemical resistance is decent. Now, the strength is here is a little lower than other glasses, but it's good at bending. For example, it's a little better at bending than other glasses. It depends again on the composition. That's why we use it. It's flexible. It has quite a few nice applications. It's good for insulation. Also, it's also used for lasers, optical fibers, and things like this. So this strength is a little unfair. Maybe 4. So green could also be good, but it's because I try to put together all the mechanical properties as it does not have an impressive compressive resistance. So sort of borderline, let's say. Okay, 3.5. A little more green than the yellow you can see here. Okay. And then something that really messes up with my drawing and is lead, because lead is it can be like aluminum and other elements can be both part of the network and stopper and interrupting the network, which makes it a valve, but it only has two connections. So to follow all the same rules that apply so far, I need to represent it like a poor lonely valve that has only one connection because the other one is outside of the plane. And this means that usually there's another oxygen connected to lead, but it's also good at interrupting the structure. And this is used in crystal. And crystal is a fairly strong, fairly soft, nice material, which has a lot of different chemical composition and is difficult to cover all in just one drawing. But basically what I want to say is that it's not extremely weak. It's sort of easy to work with because the melting point is not very high. The properties are nice, but mainly because of the refractive index. This is why we like to have objects of crystal, because of the way it sparks, the way they disperse light when it's hit by light, by illumination. So we like that the style. That is the optical properties we're interested on. We're not using much crystal in laboratory equipment and things like this because there are better choices, but it's a material that used to be very popular. If you look in your grandma's storing unit cabinet, you will find crystal glasses that no one ever used, and they look sparkling, they look amazing. Maybe they're covered in dust, so just dust it off, but it looks very nice. And that is the reason why crystal has been so popular during human history. The chemical resistance is another thing we need to discuss a little bit, because all the crystals could leach a little bit of lead. I think this problem was a little bit overestimated in the past. Maybe at the beginning underestimated, then overestimated. Well, the risk is there, but in modern crystals, crystal is not so popular anymore, but modern crystals didn't have much, didn't leach much lead, so the risk was fairly low. Okay. And last type of glass I want to cover is what we call phosphate glass. And this is a little bit tricky because usually the phosphate ion has 5 connections. So in our 2D representation, we can represent it with 4 connections, but here you'll see 3. You see 3 because of the fact that actually 2 of the bonds go to the same oxygen, and that's why that oxygen is closed. Those oxygen cannot connect to another phosphate or silicon or whatever, because all of their bonds are taken by the phosphate ion. So it's a little bit of strange. Well, it still makes sense in this representation. It's not like lead was a little worse, but it's strange to see this piping that doesn't go anywhere, right? Well, the properties of phosphate glass are probably the lowest between the glasses that we cover today, especially in terms of strength and chemical resistance. It's a very delicate material, not so difficult to work with from a softening point of view. It's difficult to make it in a good quality, but not to make it in general. And it has exceptionally good optical properties. Well, not as it's not as clear as a good fused silica, for example, but it has a very high refractive index that is useful for many optical applications. And it has a very good transmission properties in a broad range of lights. Okay, so is also in the infrared region, for example. Glasses are not always very good in the infrared region. Phosphate glass is good in the infrared region, meaning that you can shine an infrared light through phosphate glass much better than you could do the same in other glasses, which is one of the main reasons to use phosphate glasses. The other important properties of phosphate glass is that it's relatively easy to put rare earth atoms inside of phosphate glass, and this is useful when you want to produce lasers, fiber optic lasers. Okay, so this is the choice of there's a reason why to choose phosphate glass. It's also unfair a little bit that they put the low chemical resistance, because phosphate glass is a little bit stronger than other glass to hydrofluoridic acid, for example. That it's the enemy of glasses. It's the acid that usually eats glasses, but it has a hard time eating the phosphate glass. Okay, so chemical resistance is low with one specific exception. Strength is low. Softening point is low, so it's not so hard to work with, and we mainly use it for optical properties. Which ones? High refractive index, where application where we need this light dispersion, and ability to transmission window, very large transmission window, so it works also in the infrared very well, and it's good with the rare earth elements, so we can use it to make lasers. Okay, and these are the main categories of common glasses. Let's say phosphate maybe is not as common as the other ones, but still a fairly simple type of glass. The other thing I wanted to show you is how we actually make color. To make a glass colored, we need to add some other elements inside of it in different amounts depending on how strong we want the color to be. And this is something that in Venice they did for centuries. So if you add like iron or copper, you can obtain a red. With selenium erbium, you can obtain pink. Cobalt, for example, is good for blue, the famous cobalt blue. Cadmium compounds, but also silver compounds, etc., can produce a nice yellow. With titanium, we can go to like browns. Manganese and nickel can go to purple, or more manganese than nickel. Then we can have orange, we can have black, we can have green, depending on not just the element, but also the valence of the element we add inside. Okay, for example, iron can do red, can do black, and can do green, and this is basically depending on the valence of the iron we put and the amount. To make a black, we need a lot of iron, for example. And there's one more color that I want to speak about, and is obtained adding uranium to glass. And I find that this is amazing. So basically, uranium glasses are fluorescent and under UV light, and this means that you can see this nice green glowing transparent glass, and they were used to be relatively common, like at the beginning of the last century, and now they are like collectorly items that you can find in second-hand stores, and there's people going around with UV lights in second-hand stores looking for uranium glasses, and to have them at home is not really dangerous because the amount of uranium inside of uranium glass is very low, so the amount of radiation that is emitted by these uranium glass is negligible. So you can keep them in a nice cabinet and have your collection of sparkling green uranium glasses, like straight out of a Fallout video game. And I think it's amazing. I would love to collect uranium glasses. Well, it's also like festive. It feels like Christmassy, let's say. Well, this is everything for the short introduction of glasses I wanted to give you, and see you all next time. Goodbye.